Well, today's speaker, I don't think he needs introduction. He's well known by all of us. So then, without further ado, let's jump right into him. Thanks, Jose.
Sure. Yes. Okay. It's always a great pleasure to give a seminar, in particular, to give a seminar in CENTRA. Today, I'm going to talk about black holes and hot shells in the Euclidean path integral approach to quantum gravity. It's a work that has been ongoing for some time. It's in collaboration with Oleg Zaslavsky from Kharkov in Ukraine, and also with Tiago Fernandes, PhD, here at CENTRA. So I hope you enjoy what I have to talk about. So let's start wrong. Let's go here. So first, I'll give an introduction for motivating what we are doing. So we stick to the view that there are three fundamental constants. So everything gravitates, and we have the gravitational constant. Everything moves, and we have the speed of light, and all is constant. So all the other constants, we consider that they are not fundamental. Now, with these three fundamental constants, one can make a mass, a length, and a time. And they are given by these expressions, H, C, and G, so you can compose them. And they were put forward by Planck in 1900, just after he discovered that H was a fundamental constant. But actually, they were revised earlier by an Irish physicist, Stoney, in 1881. Actually gave the name electron to the unit of charge, carrier of charge. And in 1881, he also put this system, but actually E. But since E squared over HC, the fine state constant, is a constant, then we see that either E or H will do. So Stoney was 20 years ahead of Planck. But people say that this is Planck units. So to have an idea, you see that the mass of Planck is 10 to the minus 5 grams. It's huge in terms of elementary things. The length of Planck is 10 to minus 33 centimeters, which is very, very tiny, and the Planck time follows immediately. And you see, this means that, for instance, to have a black hole of 10 to the minus 33 centimeters, you have to have a mass of 10 to the minus 5 grams, which is kind of a cell mass or something like that. So, you know, things are really big and small in Planck's case. So one can put all these three equal to 1, all these three units equal to 1, and everything is measured in terms of this case. The Planck scale is where quantum gravity is supposed to take hold. So let us start with the Hawking thermal temperature for a black hole of mass m. And the formula that Hawking discovered, and I put thermal because there are many H's. So it's 1 over 8 pi Boson constants times hc cube over g, 1 over mass of the hole. So it involves three fundamental constants and the Boson constant. Now one can ask, is this formula fundamental? And the answer is perhaps yes. Now recall that Planck mass is given by these quantities here. So we can pass c squared to this T thermal, multiply by constant Boltzmann, and get kBT thermal over c squared is equal to 1 over pi mass Planck squared, that is Planck squared, over m of the black hole. So we can define the thermal mass given by this quantity here, because this is energy over c squared, so it's a mass. And can turn things around and define a Hawking cloud with Hawking mass mh for Hawking or for hole once the thermal mass is given. So you have m Hawking is equal to m Planck over m thermal times m Planck, because of this expression here. M Hawking is equal to m Planck over m thermal times m Planck. Okay? We can compare with the Chandrasekhar mass, which is essential. Some constants, some numbers, hc over g to the 3/2, 1 over the mass of the neutron, or the mass of the proton, because they are practically equal. So the Chandrasekhar mass can be put as m Planck square over m neutron square times m Planck, because it's m Planck cubed. Okay? So this is the mass of the Chandrasekhar star that we know is the maximum mass of a white dwarf. And it's also the mass of a Landau-Oppenheimer-Volkoff star, which is a neutron star, maximum mass of a neutron star. Landau worked that in 1932 with some plausible arguments, and then Oppenheimer and Volkoff, the full expression in 1939, the full calculation in 1939. So you see, if you envisage the Hawking mass, the whole mass as this, and Chandrasekhar mass as this expression, you see that m thermal and m neutron or proton play a similar role in defining the masses of mh and mc. Now, there is a tendency to say that the mass of the neutron is not fundamental, because maybe there is a fundamental theory and we get the masses directly. Well, let's be more specific. So we draw the two corresponding figures. We have the Hawking cloud and the Chandrasekhar star. Now, the Hawking cloud, you see there is a cloud of particles being emitted with all this cloud as thermal mass. And there is a Hawking mass in the center, which is the whole mass. And it's given, as we saw, by this expression here. We can also calculate the Hawking radius, or the whole radius. And if you do the calculations, you see that is the order of the wavelength of the emitted particles, lambda thermal. You can do the same for Chandrasekhar star, and you get that mass, as we have seen. So here is Chandrasekhar star full of protons, neutrons, and electrons. You can also work out the radius of the Chandrasekhar star, and it depends on the Compton wavelength of the electron and Compton wavelength of the proton or neutron, divided by the scale Planck. And also for the Landau-Oppenheimer-Volkoff radius, then instead of lambda E, you have lambda neutron, and so it's lambda neutron square of Planck. You see, you can have both here. So these expressions are similar in a sense. So why consider them of different character? So that this is fundamental in the sense that it's quantum gravity, and this is not quantum gravity. Well, the possible answer is that the thermal quantities, m thermal and lambda thermal, which are essentially the same, one is 1 over the other because of the Compton wavelengths, are statistical quantities because they are thermodynamics, thermic quantities. And so involve only quantities that enter to the system itself, which is gravitation, pure gravitation. And so only involves, even if we have a thermal, it's a thermal of, you can think of a thermal of gravitational quantities. So maybe this is really pure quantum gravity phenomena at low energy scales relative to quantum gravity. Let's put numbers. We have seen that the Hawking temperature, the thermal temperature, is 1 over the mass of the black hole. If you put the numbers for the constants, you get 6 times 10 to the minus 8 solar mass over the black hole mass in Kelvin. So for instance, for the one black hole is 1 solar mass, you can calculate the radius because it's Schwarzschild radius, gm over c squared. and you get 3 kilometers. The sun has 700,000 kilometers. So you have to shrink the sun to 3 kilometers to get a black hole. And then the temperature of the corresponding black hole, of the Hawking temperature, is 6 times 10 to the minus 8. You can say, well, and if I have a black hole with the mass of the Earth, then the mass of the Earth is 3 times 10 to the minus 6 solar masses. You get the black hole radius, which is around 2 centimeters, and so the temperature of a black hole with Earth mass is still tiny, 10 to minus 2 Kelvin. You can say, well, let's do Mercury. Well, you do for Mercury, and you get the temperature of the corresponding black hole. It's half of a Kelvin. Can do for an asteroid. A black hole as an asteroid. It has 6 times 10 to the minus 5 centimeters. Then you get already some temperature. So if you put a black hole here, you feel hot because it's 27 degrees Celsius already. Now you can think, and what about a mountain? Well, a mountain has kind of 10 to the minus 19 solar masses. The radius of the black hole corresponding to the mass of the mountain is 10 to the minus 13 centimeters, which is the Newton radius or the proper radius, and you get already a huge temperature. So it burns with 10 to the 11 Kelvin. So for mountain mass black holes, which are this and are 10 to the 15 grams, Hawking radiation makes an impact. Of course, makes an impact in masses in between, and mass is higher. So such a black hole has the mass of an Everest, say, and the size of a neutron. And it's a really interesting black hole for what we want. And so here you see, we depict the Everest with 10 kilometers, 10, 10, and we put 1 kilogram into 1 cubic meter, and you get 10 to the 15 grams. Now you compact this to the size of the neutron, so you have Everest at the size of the neutron, you get a black hole with 10 to the 11 kelvins. So these systems that are hot, in a sense, is the kind of system that we are interested. So say microscopic, and high temperatures. Quantum effects are important, but we do not need full quantum gravity. Now, if the system is a pure black hole, left by itself, it evanesces, disappears. Well, there is the breaking of the vacuum, as Hawking told us, from the strong gravitational field near the event horizon, and particles, gravitons, matter fields are emitted to infinity with the Hawking temperature, and the black hole radiates on and disappears. So to understand more deeply the conversion between black holes and the hot matter, one encloses the black hole and the hot matter inside a heat reservoir, maintain that constant temperature and the constant radius. And so we are dealing with what is called the canonical ensemble of statistical mechanics. And then a thermodynamic treatment for the system is possible. So to have an exact solution, we are going to consider that the matter, whatever it is put in the form of a thin shell. And of course, it's a huge approximation, but it permits an exact solution, thermodynamic exact solution. And now we have that the shell surrounds the black hole and is surrounded by the heat reservoir. So from now we can start the technical part after this motivation and understanding that this is the kind of system that you want to understand. Okay, so first the mechanics. Pure general relativity. We have a shell, a black hole inside. Outside the black hole there is Schwarzschild. Outside the shell there is another Schwarzschild. The shell has radius alpha, rest mass m, tangential pressure p, has its own gravitational radius r plus tilde, so it's characteristic of the shell, and the black hole has an event horizon r plus. So this, for instance, the sun has some mass and radius 700,000 kilometers, has gravitational radius 3 kilometers. The same for the shell. Shell has some mass, has some radius alpha, and has gravitational radius r plus tilde. The line elements for the inside r plus less than alpha is given by this expression here, where you get r plus here, and you get a connection so that the metric, the line element is continuous. For the outside, you get this line element with r plus tilde, and you have to fit those things to have a shell. So r plus is the event horizon radius, r plus tilde is the gravitational radius of the thin shell, and it's not an event horizon radius, okay? Now, we know that mass and the horizon of gravitational radius can be converted in spherical symmetric case. R plus is equal to m, so it can be traded. And also r plus tilde is equal to m tilde. There are two important functions that I need you to memorize, which is this function here, which of course appears here, and this function here, which of course also appears, the root of that. And at the shell there is the connecting function, and the redshift for the outside is precisely given by this function, and this is a very important function, and the redshift for inside is given by this function times b, which is also going to appear. So don't forget, k is 1 minus r plus over r, tilde, you have to put a tilde, without tilde you don't put a tilde. Now you have to see what the shell is made about. So we have to work the junction conditions in general relativity, and you get that the rest mass, which is essentially the energy density, the rest energy density times the radius of the shell times 4 pi. And then if you do the junction conditions, you get that is essentially k at alpha minus k tilde at alpha, and you get the mass times alpha. Can change and put the form, invert this and put the form in terms of r plus tilde is equal r plus 2mk alpha minus m squared over alpha, or if you prefer to put in terms of m tilde and m, then you get 2 here because it's 2 here. There is another junction condition because you have a shell, you have a gravitational field, so you have to have tangential pressure supporting the shell against gravitational collapse, and so you have that the pressure has to obey this condition, and if you do the derivatives, you get this expression here with the case, the redshift function that here already. Okay, so this defines the shell, and now we want to study and do the gravitational statistical mechanics and the canonical ensemble for black hole plus hot thin shell. Okay, so we put the system in a heat reservoir of area 4 pi r square, where r is the areal radius, and at temperature T. And so this defines the heat reservoir, okay? And in statistical mechanics, which you of course have done the course, this defines the canonical ensemble. So in the canonical ensemble, energy can flow, temperature is fixed. Energy can flow through these walls. Now we are going to put Planck constant equals to 1, Boltzmann constant equals to 1, so all quantities are referred to Planck scales.
No, these two.
Yeah. Okay. Now, a brief introduction to the way we are going to work. We know that in Minkowski spacetime, the amplitude of a field phi, say at time t1, to go into a field phi 2 at time t2, is given by the product of these quantities, of these states, and you can put as evolving the phi 1 with the Hamiltonian operator, and then cross with phi 2. Now we know that Feynman's path integral approach says that this quantity is given by the integral over all fields of e to the I times the action I of the field. Okay? So you can equate this to and say that this quantity here is equal to this quantity here. Now, we want to Euclideanize these things. So we define an Euclidean time, tau, which is equal to minus IT. Put T2 minus T1 is equal to minus I beta, with beta some quantity. And since now we have space, because it's Euclideanized time, put phi1 is equal to phi2. And what we get if we do this, perform this evaluation of this quantity correctly, is that you can, this is a matrix, you can diagonalize and get the eigenvalues, values of H, which are the energy eigenvalues. And so you get first trace of V minus beta H is equal to this integral, now with I Euclideanized, so there is a minus here. And the integral is taken over all fields which are periodic with period beta in imaginary time. But now you can recall that trace of E minus beta H you can put as a sum over all states of the system with energy I of E minus beta EI. And then you say, well, if I identify this beta with the temperature of the system, then I get the partition function of called statistical mechanics partition function. Z, which is the partition function, is equal to sum of e to the minus ei over t. So the partition function can be calculated through the path, the Euclidean path integral in this way. Okay. So we have a means of calculating the partition function for the system, and once we know the partition function, we know everything about the system, including the thermodynamics of the system. For instance, the free energy, which is the important quantity in the canonical ensemble, can be found directly by F is equal to minus T log Z. So we have, if we know Z, we have thermodynamics from this immediately. Okay, so this is Feynman and Hibb's book is all there. So Feynman found this formulation. Now, this formalism can be extended to gravitational systems, and the partition function now is formally written as the integral over the fields G and phi e to the minus I, where G is the gravitation field. Now, we know that we have to Euclideanize time, and so we have to have a space time Euclideanized, which is a space. So here we got tau and tau here for R plus less than R less than the shell, the alpha of the shell. And for this, actually, this should be R here, capital R. And what happens is that you see this, you have R and tau, and you have R squared the omega squared. So, and tau is periodic now. It's Euclideanized and periodic. And so you have here actually a sheet to space. So the topology of this space is R2 times S2. The boundary at the reservoir is, of course, the boundary is an S1, which is a circle, times R2 still in the boundary. You have for each point a sphere. So in the canonical ensemble, one has to impose a temperature, a beta or a T, because beta is equal to 1 over T. And S2 at the boundary as area 4 pi R squared. Now, it's interesting to note that once we fix the temperature at the reservoir, and we have a black hole, for instance, a black hole alone, with some temperature, then if you want to do thermodynamics, the temperature of the black hole cannot be any. It has to adapt to the T that you are imposing at the boundary. Okay? So the black hole and the hot shell, because we also have a hot shell, have to adapt to the boundary values. So the temperatures are not arbitrary, and in a sense, it translates to the avoidance of conical singularities at the horizon in our tall plane. Because if we want this to be a plane without singularities, as we want to treat a thermodynamic system has no singularities, so this has to be not conical singularities. So you have to impose some restriction on these quantities. Now, the classical action for this system here contributes to the partition function. And so at the semi-classical level, because the partition function gets an h bar here, and so when h bar over h bar, when h bar goes to 0, z is equal to 0. So even at the semi-classical approximation, one can say that, well, the geometry already contributes to the partition function. And so we want to see what happens only considering geometry and not the quantum fields that might be present. Okay, so in this approximation, one gets z is equal to e to the minus I. You don't need to do the integral because it's only one state. And so you get immediately the free energy of the system by minus 1z, which is in a sense I. So the free energy and the action are the same thing because beta it is positive. Now we have to find the gravitational plus matter action. So we can divide in the gravitational part, in the matter part, but it can be split in terms of the action for the inner part, the action for the shell, and the action for the outer part. And it is written as the Einstein Hilbert action for the inside, the Einstein Hilbert action for the outside, plus a boundary term because there is the boundary, there is this reservoir, and so you have to take care of this. R is here the Ricci scalar, of course it's not the radial shell, and R here is the Ricci scalar of the shell, and then we consider that matter in the shell has some entropy, some temperature, and the energy density, and so it belongs to that. Now, we have to treat each term very carefully and get the final action. And it's very simple, essentially. It's given by beta, inverse temperature, times the radius of the reservoir, 1 minus k tilde r minus pi r plus square minus the entropy of the matter, where k tilde is the redshift, as we have seen, and Sm is the entropy of the matter for the thin shell. Now we can argue that this has to be a function of r plus alone. Actually, can demonstrate for all this to make sense. This quantity has to be a function of r plus alone, and we call that the full entropy of the system, the total entropy. And now that we have that, the thermodynamics follows immediately because T is greater than 0, B is greater than 0, I and F have essentially the same content. So we can use I because we are making that. Okay. Now we can find the thermal energy and temperature. Thermal energy is direct of the systems. So it is the differential of I in relation to beta are constant, and you get this expression. The temperature, we note that it is fixed at the boundary, T. And we have to impose that there is no conical singularity in the Euclidean 2 manifold, R tau. Then we get that the Hawking black hole temperature, which is essentially the inverse Hawking black hole temperature, and the redshift functions of everything have to adapt to get T. Okay, so this is the same as here. K is this, K tilde is this. Okay, so we get an expression for R plus in terms of r plus tilde, so the horizon radius of the black hole inside is a function of r plus tilde of t and of the shell radius alpha. And as we will see, the horizon, the gravitational radius of the shell is a function of RT. So R plus is a function of RT and alpha. Now, it's interesting to note that in this formulation, the no black hole case cannot be taken because R plus is equal to 0, T diverges, T is constant. So you cannot take that. And then you have to go back and say, well, if there is no black hole, I have only a shell, and then do the thing. It's not very difficult, but you have it's not a particular case. And it's meaning that disappearance of a black hole, if you have a black hole and it disappears, it's not pure flat space-time because it leaves a defect, at least in this approximation. Now you can make use of the Tolman relation for the temperature, stratification, which says, for instance, that temperature at the shell times the redshift at the shell is equal to the temperature, fixed temperature at the reservoir times the redshift at the reservoir. And then using this relation, you get that the temperature at the shell is 1 over 4 pi r plus k alpha.
You're not assuming there's any back reaction. So the black
Only-
hole is
only-
radiating, but it keeps its temperature.
On
Only the shell.
semi-classical everything. Now we obtain a very important feature of the system. We have seen that the entropy is a function of R plus alone. So we can differentiate that and get, well, that the differential is a function, R plus, okay? Now, the action E from the action principle should be stationary with respect to R plus. And so dI, dR plus is equal to 0. So if you go back to the action, it was that formula beta R minus, you get this expression here, and you get that the inverse temperature is that function here of R plus alone times K tilde of R, the redshift function. You can invert and get T is equal to 1 over B of R alone, K tilde of R. You can put as a T naught of R plus, defined as 1 over B. So you can call this B, which is a very important function. So it's not everything that enters. Beta, as a function of R, R plus has to be split in this way. That's mandatory for the system. And so B, which is a reduced inverse temperature equation of state, or T naught, reduced temperature of state, enter into this formula in this way. Consequences. T is fixed, R is fixed. So what happens? This means that not all R plus tilde are solutions of the problem. Only those, you give an equation of state, and only those, so this is free, but only a function of R plus tilde. Only those that fit into T and R solve the problem, okay? So it gives an equation for the possible gravitational radii R plus tilde of the shell. So R plus tilde is a function for each T and R is a function given here. Now, the meaning of T naught, it's also interesting because at infinity, this, let's say this, you can suppose that you have the reservoir and then you have radiation and let some radiation go away and go to infinity. And then you get a K tilde, which is 1. And so the meaning of T naught is, let's say, a temperature at infinity for some imagined radiation that can escape the reservoir and goes to infinity. And so it's equivalent to the Hawking temperature for a black hole. But now we're dealing with a shell. Sorry?
You have a boundary value fixing the reservoir, right? radius r, temperature t. So what you really have to find is on the phone. That's why you're getting energy levels. Like it's like in quantum mechanics. So
That's right.
atoms, that's what you get.
That's right. Yeah. So now we can work out the entropy of the system. We saw that there are two terms in the action, and one was pi r plus square, and the other was matter entropy. Now, this pi r plus square is, of course, the black hole or Bekenstein-Hawking entropy, because it's 1/4 of the horizon area. And from the stationary principle for the action, recall that the action was this, one actually finds that this is constant, this is E, so this is dE, this is S. You get d beta d minus ds is equal to 0. Beta is 1/t, so d minus ds is equal to 0. And so we get immediately from this formalism the first law of thermodynamics for the system. You can develop now these quantities and get the entropy. And actually what you get is what we have seen already, that the entropy is given by this equation, and it has to be, because the entropy is an exact differential. And so there is no other way that to have a thermodynamic system that we can have a different quantity. Okay. What is really interesting is that we can find then what is the matter entropy. You play around with these things and then find that the matter entropy, so the entropy of the shell, let's say, is given by the integral from r plus, the horizon radius, to the gravitational radius of the shell, of the function that you choose for the shell, the equation of state for the temperature of the cell. So this is really a precise and remarkable result. And you can also work out the first law for the shell, and it obeys the first law, which is also surprising because this is for the system. But then if you check if the shell obeys the first law, it obeys. And you can also work out the first law for the black hole interior, and it also obeys the first law. So we managed to get 3 first laws of thermodynamics for the system, but the important one is, of course, for the whole system. Now we have to see the system stability of the black hole in hot thin shell. And this is given by the heat capacity. So we know that it is stable if you give more energy, the temperature increases. And if you give more energy and the temperature decreases, or vice versa, it is unstable. You know E, you can make this derivative, and you get this expression here. Now, this means that this quantity has to be greater than 0. You can now change for R and see that for the systems to be stable, capital R has to be less than R plus tilde plus B over 2P dash, derivative of B in this way. For instance, you can say, let's give an equation of state, which is a power law. These quantities here determined by the matter in the shell itself. Then you get this heat capacity, and so you find that there is stability if R is less than 1 plus 2 delta over 2 delta R plus tilde. Okay? So depending on delta, R, the radius of the reservoir can be as big as you want. Okay, now, I think we have to go to the most interesting part of the work, which is an exact solution, thermodynamic exact solution, and actually found the thermodynamic phases for this system. So what is the simplest equation of state that you can think of? Well, it's the Hawking temperature equation of state, but not for the shell. So you give that the inverse temperature is 4 pi R plus tilde. And then, so this is, we choose what we want the shell to be composed of? Well, it has a sigma, it has some pressure, and it has this temperature. Okay, and then you find that the action now is minus pi r plus tilde squared times this term that was there already. The thermodynamic energy is still the same. The entropy of the system now you can calculate, and is actually 1/4 of the area of the gravitational radius of the shell. It's not a black hole, it's the areas of gravitational. So it's the Bekenstein-Hawking entropy now for the shell. Okay? Can also play around and find that free energy is really E minus ds, as it should be. Now, as I said, there is an exact solution for this. So we have the reservoir, we have the shell, and we have the black hole. So we want a solution for the exterior quantities. So given this B, we can calculate the possible gravitational radius r plus tilde for the shell. And they are taken for this expression that I showed you before, which is related to the temperature of the system, has to adapt to the boundary values RT. And so it's a cubic for r plus tilde. What we find? We find that for 0 less than RT less than 4 root 27 over 32 pi, this is one over 8, but for convenience I write it this way, there are no solutions. No solutions for small RT. Then for root 27 over 32 pi less than RT, we have two solutions. It's a cubic equation. One is there r plus 1. You can write the solution, but it's a cubic, so it's not very beautiful. And the another one is there r plus 2. And here the r plus 1, it's a small solution for the gravitational radius, and r plus 2 tilde is a large solution for the gravitational radius. These solutions are the equivalent of the horizon radii found for black holes by York back in 1986 in an extraordinary work of York. But now we found that for shells and not for black holes. Well, there is another possibility for the solutions that you have nothing. So everything goes away, you have flat vacuum, hot flat space inside the reservoir. Now you can work also the interior solutions. You have, don't forget, you have a black hole inside. So you have to know the radius of the black hole inside. And for that, we have the equation that there is no conical singularities. So you get that expression for R plus in terms of R plus tilde. Now it's easy to see that one solution is that black hole radius inside is equal to the gravitational radius of the shell. And so it means that it eats the shell. There is no shell. So it's a black hole, and it is the black hole solutions found by York. Okay? But surprisingly, there is another solution, this one really for a black hole inside the shell, because this is a cubic equation. So it has one solution, and actually it has another. The other is complex. So it is R plus 2 is given by this expression of minus R plus tilde and this. And actually it's a black hole inside the shell. Okay? There is yet the other possibility that I told you, which is no black hole inside, but that you have to work out separately because the limit does not give that, but you can do that. So you have that. Now, thermodynamic stability for this system. You have that for 20 root 27 or 32 pi is less than RT. We have two radius for the shell, R plus 1 and R plus 2, one small and large. Thermodynamic stability for this equation of state that we are considering, then you have that the heat capacity is greater than 0 if the radius of the shell is less than 3/2 of R plus tilde. And so the heat reservoir has to be at or inside the photonic orbit so that the whole system is stable and makes sense. Now, we have solutions that are unstable, which is the heat reservoir and the small r+1, and we have solutions that are stable, which is the heat reservoir and the large black hole obeying this, which is precisely the r+2 solution. Now we can study the phases. F is the important quantity, but F and I are the same thing. So we know that the systems left by themselves tend to lower F, as in the canonical ensemble, as systems in the microcanonical ensemble with fixed energy tend to higher entropy. So in the canonical ensemble, the system with lower F. Don't forget F is equal to E minus ES. So S has a minus sign. And so we have to see which phases that are possible have the minimum possible F. Well, the r+1 tilde is of no interest here because it's unstable. It has other interests, but not here. The value of r+2 tilde is independent of whether it is a pure black hole solution that we found or it is a shell with a small black hole inside. So we can say that pure black holes and hot shells, if they are possible, they coexist in the ensemble. On the other hand, if you have hot flat space, so the reservoir with nothing inside, only being hot, one has that, there is nothing. So the action is zero. So we can check that. Now the root 27 does not appear, but appears the 32. That's why I'm maintaining 32. Now, if 27 over 32 pi less than RT, less than RT essentially, then the action for the large black hole is less than the action for hot flat space. And the action is the free energy. So this phase is preferable to hot flat space phase. And so what we have is a hot shell with or without a black hole inside. Because now we have to see if you have a hot shell. Actually, it's a hot shell or a black hole, depending on the solution. So both coexist in the ensemble, as I said here. Now we want to analyze if we have a hot shell for this equation of state. We are still for pi r plus tilde, not for any equation of state. We want to analyze if a black hole inside or nothing inside is what we want is preferable. But we have just seen that the action depends only on the gravitational R plus. So to have the action of the shell with a black hole inside and the action of the shell without anything inside, the action is the same. And so the non-existence of a black hole inside makes no difference for the action, for the free energy. So the two interior phases coexist in the ensemble. It's another degenerate state, is one for the interior. So summary of these phases. There is a drawing which is easier to understand. You fix RT at the reservoir, and if RT less than 27 over 32 pi, then there are no black holes, only hot flat space. If RT is greater than 27 over 32 pi, what you have in the ensemble? 50% of the systems are going to be pure black holes, and 50% of the systems are going to be hot shells. But then, within the hot shells, you will find 50% with a black hole inside and 50% with nothing inside. Now, this is really interesting because an observer perching on the heat reservoir cannot distinguish thermodynamically between these two states. And so the hot shell is a thermodynamic mimicker. People found, and actually I've also worked with dynamical and geometrical mimickers of black holes, for instance, quasi-black holes. But here is a new mimicker. It's a thermodynamic mimicker. They don't need to be quasi-black holes, man, something like that. Yes.
What do you think of the central image and the right moment?
Huh?
Yeah, that one and the bottom one. If you look at those as two limits of the uppermost figure.
Two different what?
Limits.
Of what?
The top figure.
Yeah, but that was a solution. Precisely, we found that in the solution. There was a solution. Yeah, that's right. And actually, it is in the solution. Well, too many things to say. Actually, in this solution, you found this independently, but this solution, if there is a limit that you go to there. Okay, and you get that one, which is really interesting as well. Okay, there are other additional important results, but you see there are too many results, so let's pass to the conclusions. So in fundamental physics, everything is quantum. In particular, the states of a thermodynamic system are quantum states. For thermodynamic equilibrium, it is represented by a maximal mixed state described as an ensemble. And Feynman revealed how in a system at fixed temperature, and so in the canonical ensemble, you can Euclideanize space-time and get physical theory and get the concise description of the system, in the case of the thermodynamic system. Hawking, after discovering that black hole radiates and all of that stuff, that the analogy between black hole mechanics and thermodynamics, applied this formalism to black holes and showed that gravitational statistical mechanics and black hole thermodynamics are extremely important in the understanding of this physical phenomenon. These understandings depend on the Euclidean approach, as we have shown here. The geometries, the four geometries that are Euclidean that appear, and in particular the topology. Topology itself is of great importance in all the phenomena, and clearly it brought these topological issues right into the heart of quantum gravity. That was already speculated by Wheeler and those wormholes, but Hawking showed in a precise way that maybe topological issues are very important. Now, Hawking, in a sense, got it all wrong because the system is not stable that he found for the black hole case, not for the rest. The system is not stable, and so there is no sense in treating thermodynamic unstable system in this way. But then York in '86 put out that, well, we have to have a heat reservoir because heat reservoirs are the correct thing to have in a canonical ensemble. So we put a heat reservoir and studied precisely the Schwarzschild problem with the necessary and boundary conditions. Here we have added hot matter in the form of a hot shell to the black hole geometry. And we have found that we were able to compare in the canonical ensemble a black hole phase with a curved space hot matter phase. Of course, this is of interest because black holes have mass, space is curved, and so if they evaporate, you have matter, and space should also be curved. And so we managed to, at semi-classical level, to understand the phenomenon of transition between black holes and matter. Essentially, we expect that matter will be made of hot gravitons or photons or particles. And we said, well, let's put everything in a hot thin shell and try to understand the thermodynamics of that. We have seen that the matter temperature equation of state, which is a free function of R plus, of course it has to be physical, is of the utmost importance and essentially dictates the whole of physics of this canonical ensemble. We have found a new black hole mimicker, now a thermodynamic black hole mimicker. Information about what is inside the reservoir is not explicit for an observer on the boundary, on the heat reservoir itself, studying thermodynamics of the system. And of course, this mimicker is to be added to the well-known set of dynamic and geometrical black hole mimickers. As we stated in the introduction, this approach is valid for microscopic black holes, let's say for size or bigger. And it will be interesting, or smaller, it will be interesting to have these tiny black holes in laboratory, if we can do, and test the features found here, in particular the behavior of the thermodynamic phases. I would like to tell you that I've been working at it since 1996, where I tried to apply York formalism to the black hole, the two-dimensional black hole that I first found before in Untitled Chapter theory, which is a two-dimensional theory that is now in vogue, but almost 30 years ago I was already working at it. And then with Claudia here at the IST, and with Gonçalo Dias and Zaslavsky and Rui André, all of these were students, Zaslavsky's collaborator. We try to understand either in the Euclidean path integral formalism or in the direct Lorentz formalism, so through the Hamiltonian treatment, these systems. And we have now work ongoing with Zaslavsky. So this work that I present is going to be sent soon to publication. And with Tiago Fernandes that understands now all of these systems, perhaps better than me. And also with Rui André, that was a student here until 2 years ago, with a PhD. And we have this paper pending, but it's going to be published one day. So I thank you for the presence.
Thank you much, Jose, for a nice talk. And we have questions.
So, I had a question about these thermodynamical black hole mimickers, and I'm wondering if, at least in principle, you can use the entropy to distinguish with the situations. So if I remember correctly, it's a black hole versus a black hole encased within a shell. So you have the entropy of the shell and the entropy of the black hole. But I think can't the entropy be used to distinguish them from the dynamic?
No, it only depends on how close to it. It only depends on the gravitational radius of the system. For one is gravitational radius, for the other is horizon, but they are the same. Okay, so thermodynamics cannot distinguish.
More questions?
No, George, to change.
So there are obvious similarities between the thermodynamics system that we studied and black holes in ABS. ABS, there's also like box. And also study the and Page did that.
No, actually, I did that. I know that Hawking Page did that, but they did in the microcanonical ensemble, because that's the you see, thermodynamics of Bryce and Hunt consider black holes in the grand canonical ensemble. So we actually did that. And using this formalism. So we put ADS and we put a boundary, not at infinity, somewhere, and studied what were the possibilities of that. And of course, the first thing that we did after we had the expression result was, well, take the boundary to infinity and get Hawking and Page. We did that and we got Hawking and Page. So Hawking and Page, of course, we got also several phase transitions here as Hawking and Page. Hawking and Page was, they managed to understand, no, what they did was, Hawking was worried that he could not do thermodynamics with the path integral, because everything was flawed, stable. But then he said, well, with the Untitled I can do it, but I have a model. So they did quantity simple. And this is before, I think it's before York 86. I'm not sure, but I think it is before. I think it's 84 or 82. So, yeah, of course. But antideceiver you get, here you have your own boundary condition. Antideceiver, it's different boundary conditions, completely different boundary conditions.
But you get the same kind of results as also in that case, there's a large black hole and a small black hole.
That's right.
The large one is stable, the small one is stable.
That's right. That's right, but that's you have there a normal, a natural boundary.
So, I mean, just this question. Anybody else have any questions? Otherwise, okay. Just George again.
Well, I guess maybe this is a naive question, but I guess out of curiosity, if you could allow for a conical singularity in the RT plane or an RTAL plane, and then you would rotate back to real time, what do you get?
Well, you get if you get black holes with singularities, probably. So
Like on the
so you get with the horizon is singular. So surely you get black holes singular at the horizon. Well, in full quantum gravity, maybe they pop out in a sense. Out of all this, you can get this kind of black holes with conical singularity. So.
sounds like
But yes.
The solution to which you have two shells that are plus one, not plus two. Like that. The one that is unstable, thermodynamic I think you disregard that. You could have a black hole with two shells in equilibrium. No. One at R1 and one at R2.
No.
Why not?
No. Okay. No, you can. You can. That's different. It's a different problem. I think that's a different problem. Then you have to work out the junctions for everything like that, and so it's a different. I don't think. What? Which case?
Would you put the shells exactly at those two equilibrium points?
Not sure. No. I don't think you can put the shell at the black hole because inside you have flat space. So I think that maybe you are seeing something that I'm not seeing, but I think then it's another canonical. So.
These were valid after you imposed the equation state.
Sorry, this.
You imposed a certain equation state.
For generic, you have also worked out generic state. Have some results on that, which are generic as well. But this one was very simple, but beautiful because we have two solutions: pure black hole and shell. And Gary is working on other equational states. We have 4 solutions. Yeah. We have several solutions. So that's right.
Yeah, so we already passed the time, so unless there's a very, very short question, which is not the case, then I suggest we start our speaker again.
If you enjoyed the video, like and subscribe.